All right, so now we can prove the thing that you wanted to a while ago. So we can prove that Cauchy sequences converge. So remember, we proved that convergent sequences are Cauchy, but now we can prove that Cauchy sequences converge. Remember, Cauchy sequences don't make a reference to their limits. So this is a way of knowing that a sequence has a limit without having to know what the limit is, which is very, very nice. Okay, so here is the first lemma. The lemma says that if, let's suppose that I have a Cauchy sequence, is Cauchy, and a subsequence, let's call it A sub nk, where k is n, converges to, let's call it A. Then my original sequence converges to A as well. So this says Cauchy sequences are really nice. It says that if I had a subsequence that converges, then my original thing did too. And remember, you can think about this as being kind of like what we proved for convergent sequences. We showed that all the subsequences of a convergent sequence converge to the same limit. So this says if I have a convergent sequence and I have some subsequence converging to some limit, then that limit is just the limit of my original sequence. All right, so let's prove this. All right, so given this epsilon bigger than 0, I know that there is a k. Let's say a k and n, so that if lowercase k is bigger than the capital K, we have that A sub nk minus A is less than epsilon over 2. And this is just using the fact that the sequence converges to A. Okay, and also there is an n, so that if little n is bigger or equal to big N, we have that, well, let's just say something slightly stronger, that if n and m are both bigger than or equal to big N, then A sub n minus A sub m is less than epsilon over 2. So this is using that the sequence is Cauchy. Okay, so taking the maximum, let's say m to be the maximum of n sub k, n sub capital K and n, we have that if we have that if n is bigger than or equal to m, well, we have that, first of all, we have that A sub m minus A is less than epsilon over 2. Okay, very good. And that's just because of this thing here. Okay, and then we also have that A sub n minus A sub m is less than epsilon over 2. And that's using Cauchiness over here. Okay, so by the triangle inequality, we have that A sub n minus A is less than epsilon. I'm just adding, that plus that gives me A sub n minus A. So I proved that given any epsilon, there is some capital N, that if I take all little n's bigger than or equal to capital N, the difference between A sub n and an A is less than epsilon. So I've exactly proven that if my sequence is Cauchy and it has a convergent subsequence, the sequence converges to that also. Fantastic. Okay, so now we can put the pieces together and prove that Cauchy sequences are convergent. So here is the big theorem. This theorem probably should have someone's name attached to it, but I don't know. I don't know whose name I would attach to this one. But let's go. But this is probably like the biggest theorem we've proven so far. So we've proven that a sequence is convergent if and only if it is Cauchy. Okay, so now that we've done all this work, it's pretty easy. So let's see. So first, recall. So let's suppose we have a Cauchy sequence. Okay, by the previous video on Cauchy sequences, is bounded. Okay, so then by the video on subsequences, or I guess we named this theorem the Bolzano-Weierstrass. So by the Bolzano-Weierstrass theorem, it has a convergent subsequence because we said that bounded sequences had convergent subsequences. But now, by this lemma, we said if we have any subsequences that converges, then the original one does too. So by the lemma, and where n is an n, converges. Okay, so this showed that Cauchy sequences converged, and then we showed earlier that convergent sequences are Cauchy. Okay, so I can't stress how awesome this theorem is. So now we have a way of showing that limits of sequences exist without having to talk about what the limit actually is.